The second talk in this session is a strong call by need calculus. It will be presented by Thibaut Balabonsky, and this is a co-authorship with Antoine Lanco and Guillaume Melchion. Thibaut will present, so the floor is yours.
Okay, thank you, and good day all. So this strong call by need calculus is the joint work with, as Sylvia said, Antoine Lanco, who is a PhD student, and Guillaume Melchion, a colleague researcher at our new formal methods lab. And this also follows the previous joint work with Delia Kessner and Pablo Barenboim, Eduardo Bonelli. And all this is about the operational semantics of the lambda calculus, that is about computing with lambda terms. So as Axel said just before, the lambda calculus is a model of functional programming languages, which we might want to make one thing precise, that if we take one term, the lambda calculus, as the example we have here in the upper left corner, there are actually a lot of possible ways of computing with this precise lambda terms. And all these possible ways of computing correspond to what we call evaluation strategies, that are ways of choosing which redexes should be reduced and in which order. And so, for instance, most programming languages are using call by value, which is the path in orange here, which is characterized by the fact that in a function application, we first evaluate all the arguments and then only apply the function. This is the strategy Axel was studying. Another kind of opposite strategy is called by name in violet here, in which we do not evaluate the arguments at the beginning. We just apply the function and then evaluate the argument if and when they are needed. One difference between these two strategies is that in call by value, we might evaluate some arguments which are not actually needed, while this never happens in call by name. But the drawback of call by name is that it may evaluate some arguments several times. So here we have, in this example, the first argument is not needed, and the second argument is evaluated twice if we take the call by name strategy. And then finally, call by need, which is a strategy you can find in Haskell, for instance, optimizes call by name by adding some other mechanism to avoid the duplicate computation. And we will speak more of this mechanism later. A common point between all these strategies is that evaluation strategies are concerned with evaluation that is producing values. A value in the lambda calculus, that's just a lambda abstraction with anything inside. So in this setting, we do not care about what is inside a lambda abstraction. We do not even reduce what is under a lambda abstraction. We operate in what is called weak reduction. And the fact is that these values are not necessarily normal forms. We allow anything to be inside the lambda abstraction. And so these evaluation strategies are perfect for providing a semantics to functional programs, but they are not enough in some applications where we can need to compute normal forms. Think, for instance, of proof assistance, or in some cases, compilers. So this work, or this line of work, aims at providing strong reduction strategies that are able to produce normal forms, to truly normalize lambda terms. The topmost priority in our list today is to find a strategy which is complete, that is, that always finds the normal form whenever there is one. This actually contains already two parts. To find the normal form, we first have to reduce enough. We do not want to stay stuck midway in the path to the normal form. But also, we should not reduce too much and say, for instance, diverge by trying to reduce some part of the term which is not actually needed to compute the normal form. So this is already a quite complex statement. And second, we'll see try our best effort to sharing this calculus, that is to avoid duplication of redexes and to be at least as good as call by value and call by need usually are. And finally, since this is likely to be fairly technical and to involve a lot of syntactic reasoning, it's kind of work where a mechanized formalization using a proof assistant would be really interesting. Let me give a few more words on our goal of completeness. Call by value is exactly what we don't want for as a starting point for this, because in call by value, we will evaluate all the arguments of a function from the beginning, and maybe some of them are not needed and will have some bad influence and will prevent us from reaching the normal form. So our compass will be to reduce only needed redexes, that is, redexes which we cannot avoid, redexes which are necessarily reduced in any reduction path to a normal form. There is just one very small problem, that neededness is not a decidable property. So too bad for this work, but hooray for the infinite research opportunities. And so we'll have to find approximation of neededness. And it happens that call by name and call by need are exactly that. Call by name and call by need are built on a simple syntactic criterion that allows to find some needed redexes. Not all of them, of course, but some of them, and along the reduction to discover more and more. And in the end, we find enough needed redexes to complete the evaluation of the term. And so what we want to do here is to extend this, but to strong reduction and to normalization. Last preliminary words on the mechanized formalization. In this work, we use the proof assistant Abella, which is built on a nominal logic to ease reasoning on terms with binders. So we can define a type of TRM here representing lambda terms and provide constructors for building lambda terms. So here I have two constructors, app, which takes two terms as parameters and produce an application term, and apps, which produces an abstraction term, taking as parameter a function from terms to terms. So with this construct, we can build some lambda terms as one given in example here. You may have noticed that there is no construct here for variables. The fact is that this type of term is actually open-ended, so we can, on demand, introduce new symbols that are assumed to be fresh names, and the nominal logic of Abella gives to keep tracks of all these new elements and allow to handle them quite smoothly. And so once we are here, we can define reduction relation as inductive binary relation on terms. So maybe one side remark I can make at this point is that in call by need, using a direct inductive definition of the reduction relation is not what is commonly done. The traditional presentation uses basic reduction rules and some notion of evaluation context. And well, Delia has been asking me for years whether we could actually get a direct inductive definition for this reduction relation. I always answered that no, I don't think so, because this or that. And well, it happens that once there is no other choice, in fact, we can do it. And of course, this was a good idea. So let me now review call by need, the usual weak call by need, with all this in mind. And for this, I will take an application of one term to another, and let's see what usually how call-by-need deals with it. So first step is to evaluate the function, the left side of the application. So this is a very simple inference rule, which is here on the right, and which is translated below in Abella. So in Abella, you can see I write first the conclusion and then a list of premises. But otherwise, the translation will be quite straightforward. Once the function side is evaluated and we get a function on the left, we can establish a link between the variable x of the function and the argument u. So this link here takes the form of an explicit substitution. We could also use a let, this is exactly the same thing. And we have so this new syntactic construct. Then we do not evaluate the argument yet. We start by evaluating the function body, which is now just a term on the left of an explicit substitution. And if at some point we find an occurrence of the variable x of the substitution, then and only then we will evaluate the argument u. And once this is complete, once we have a value in the substitution, then we can just look up its value each time we need it. So it's really a lookup operation. It's one occurrence at a time. So we also call this a linear substitution. So to sum up, how call-by-need works, in case of an application, we always reduce on the left, but never on the right. We never reduce under a lambda abstraction in weak reduction. And in case of an explicit substitution, we evaluate on the left under the substitution, and we evaluate the argument only if and when it is needed. So now let's try to extend this to strong reduction to try to build normal forms. So here is a lambda term. It is a value, but not a normal form. So it's starting with a lambda, but it still contains one redex, which has to be reduced to reach the normal form. If you take a look at this redex, you can observe that it is under an abstraction and on the right of an application. That's exactly the two cases in which we said never do this in weak reduction. So obviously we'll need additional rules, we'll need new criterion to find more needed redexes if you want to perform normalization. So adding some possibilities of reducing under a lambda abstraction, that's not hard, that's not that hard, but knowing when to reduce on the right of an application, this is quite subtle. So why is that? Remember that if we have a function applied to an argument, it is possible that the function will not use its argument, it will erase it. And so maybe the argument is not needed and it should not be reduced beforehand. And this holds for an argument function, but also for the argument of anything that might become a function at some point in the future. On the other hand, if you take, for instance, the application of a free variable x to some term t, the free variable does not reference anything. It will not be substituted. It is here forever. And so the argument t will also be there forever. So it can, and even it should be reduced if we want to compute a normal form. And this, again, is not only for a free variable, but for any variable for which you can determine that it will not be substituted by anything. So our main criteria will be to allow a reduction on the right of an application in argument position of structures, and structures that will be an application. We start with a variable that cannot be substituted. These variables are called frozen. So as I already said, free variables are frozen, but there are other cases. Suppose you have a lambda abstraction for which you can determine that it will never be applied to any argument. And if it is not applied, there will be no beta reduction. The variable will not be substituted, and then the variable is also frozen. Now, which kind of lambda abstraction are guaranteed to be never applied to any argument? There is again one very simple case. If your whole lambda term, the lambda term you're considering is starting with lambda abstraction, this abstraction will not be substituted, will not be applied. It's the top level position of your term, and it will stay there forever. But that's not the only possibility. There are other positions which we call top level like inside terms, for which we can guarantee that the lambda will not be applied. And this is the case, for instance, of the argument of structures. So the key here is to identify structures, frozen variables, in top level like positions. And so for this, we will add parameters to our reduction relation, parameters that track this context information. So these two parameters are a set phi of variables that are known to be frozen at the current position, and a Boolean flag mu, which indicates whether we are at a top level like position or not. So these information are fixed at top level. So top level is a top level like position. So far, so good. And at top level, we can consider that all the variables that are free in the term are frozen variables. And then this information will be updated in the inference rules for the reduction. So let's see how we can extend our previous rules to this setting. In the case of an application, reduction on the left part is still always possible. But since the left part is applied, it's definitely not a top level like position. So we have a bottom modality for this flag mu in the case of an evaluation reduction on the left of an application. Now, on the right of an application, which was previously totally forbidden, it is now allowed conditionally, that's only in argument position of structures. But in this case, we are at a top level like position, and the top modality here. In case of an abstraction, which were also previously forbidden, this time it's always possible. We allow it unconditionally, but there is one subtlety which requires having two distinct rules, that if we are at a top level like position, if this abstraction is at a top level like position, and only in that case, the variable x is frozen. So it is added to the set of frozen variables, and there is also in the Abella code hypothesis frozen x, so you can see here. Now, finally, the case of substitutions, it's almost the same as previously. Maybe the point that we can note in that when we are evaluating inside a substitution, the argument of substitution, when it is needed, we evaluate in not in top level like position, because the destiny of this argument is to be substituted somewhere, and we maybe do not know what is the status of this position where it will be substituted. So we stay conservative and say this is not top level like. So this is a simplified version of the strong call by need. There are actually a few more things that you have to take into account, so you can see the full story in the paper. But let me just give an overview of a few elements that are missing. First, I use in these rules a needed variable predicates, and it's defined exactly the same way that the needed regex is. And so to avoid replicating the inference rules, we have one global set of inference rules with a third parameter rho, which indicates whether we are actually performing a reduction, and in this case, which kind of reduction, or if we are just probing the term for the presence of variable. And then there are also the fact that explicit substitutions can be found everywhere in the terms. And so we have to adapt the reduction rules so that they are not blocked by explicit substitutions, as this corresponds to the sigma equivalence that has been mentioned by Axel previously. It's also, we have to enrich a bit the definition of structures or frozen variables to take this into account. But what it is all deduced from the basic arguments I already gave you. And so with all this, we get a strong call by need calculus with very nice properties that I will review now. First, and this has been fully proved in our mechanized formalization in Abella, the strong call by need calculus is sound with respect to the lambda calculus. That is, any reduction in our calculus can be simulated by plain beta reduction in lambda calculus, and also that the normal forms correspond in both systems. We also have a bit more original completeness property, which ensures that each time we start from a lambda term which admits a normal form, then we will find this normal form, and any reduction path in our calculus actually reach this normal form. So we have a strong notion of termination. In some sense, our calculus turns weak normalizations around the calculus into strong normalization. This kind of completeness result is traditionally quite complex, and proofs are quite complex and may involve very intricate syntactic lemmas. But there have been a lot of progress in the last years on using intersection types, and especially non-idempotent intersection types, for reasoning on this. And actually, we build on this technique to have completeness for this calculus. So in non-idempotent intersection types, so it's quite similar to the type system also presented by Axel just before. A variable will be associated to a multiset of types, so with possible redundance. This one is non-idempotent. And when we type a function, we'll have on the argument part of the function a multiset of types corresponding to each possible use of the variable of the function. And then when we are typing an application, which is the rule I gave here as an example, we'll have one typing derivation for each possible use of the argument. And what is important, and I think this is the difference with the talk just before, here it's possible that there will be no typing derivation for some argument. In the case, this argument is actually not used. So there are several known properties on these systems, and you can see works by Philippa Gardner, Daniel De Carvalho, Delia Kessner, and many, many others. And two properties that I'm interested in here is that first, this type system will characterize weak normalization in the lambda calculus. And second property is that if we reduce only type subterms of a type term, then termination is guaranteed. And so the final step we add here is that we prove that in our strong Kolbeinit calculus, our reduction rules allow reduction only of typed subterms of a type term. So if we take any lambda term which admits normal forms of lambda calculus, it is typable, then our reduction strategy or reduction calculus will reduce only needed redexes, will reduce only typed subterms, then reduction will terminate, we will reach a normal form. And by the soundness results, we know that these normal forms correspond to the actual normal forms of the lambda calculus. One interesting thing we found during this is that, when you are typing a lambda term, usually, the type gives you a high-level overview of the structure of the term, but does not tell a lot of the internal structure of the term. Here, we learned that if our terms are frozen variables, that is variables which will actually participate to the structure of the term, then their types will appear in the global type of the term. Now, I don't know how profound this is, but it's surely interesting. Now, last point today, I would like to emphasize on the fact that strong reduction is not only about normalization, but also about optimization, about better evaluation. If you take this example, I have a lambda term, a function lambda x, to apply to some argument, which is already a value, but which is not a normal form. And if we first reduce a redex, which is inside this value, then we'll have such a reduction path here on the right. Then we'll have a shorter path to the result, and we have some optimized reduction strategies. So we could say that to be more efficient, we'll substitute only normal forms, but that's not exactly what we want, because if you take here the second example, you see you have a lambda y, y omega, which is definitely not a normal form. But still, we want to be allowed to substitute it, to go on with computation and to find the normal form of the whole term. And the point is that in our calculus, if you look at this value, lambda y omega, it is inside the substitution that is not a top-level position. So the variable y is not frozen, y omega is not a structure, and the reduction of omega is not allowed by your strong call by need calculus. That is, if you take it outside of context, lambda y omega is not a normal form, but in our calculus, at this position, it is locally in normal form. So we have a notion, an intermediate notion of local normal forms. And if we restrict the calculus by allowing only substitution of local normal form, then we still have all the good properties of the of the general calculus that were still correct and complete with respect to the lambda calculus. But we also gain additional properties, for instance, the diamond property, or we can also prove that normalizing reductions are of minimal length with respect to the full lambda calculus. So let's conclude. This was a work about computing normal forms, reducing only needed radixes in lambda terms. And so we derived the calculus, proved nice property of the calculus, but along the way, we also learned a few very interesting things. And when I say we have learned, I mean Antoine, Guillaume, myself, and I also hope I will count some of you now. First thing is that if we want to perform normalization, we need a deeper understanding of necessity of what a needed radix is. And thus this requires identifying some structures in the lambda terms, and for instance, identifying variables that cannot be substituted. Second point, intersection types are a very powerful tool to deal with termination or even complexity properties, and it really gives more elegant proofs, and you really should take a look at this if you are not already familiar with them. And well, finally, if we switch from a presentation based on evaluation context to a direct inductive definitions, we actually get a clearer theory, a simpler theory, and really more elegant proofs. And this also enables mechanized formalization. So that's really something we should try to do each time we can. Okay, thank you. If there are any questions, I would be happy to answer them.
Thank you very much. Thank you very much for the talk. We have time for one or two quick questions from Vincent van Ostrom. Could you prove ordered local commutation directly to get your optimality result? Or what would be the difficulty? It is a complete method here, I guess. See random descent paper.
Okay, I'm not sure. I haven't tried this yet. Since for now, we are mostly relying on a notion of neededness and identifying some, proving that if we since our calculus is only performing needed reduction, delaying substitution, delaying duplication is always a win. So we are more relying on this kind of meta argument for now. But yeah, maybe this would be a nice way of having a different proof, and maybe this also will be a better way of making it fit into the mechanized formalization. So I definitely have to take a closer look on this particular example. Yes.
Okay. Still, we have one more question.
No, we didn't. Sorry, I just read the question in the chat. Isn't? Okay, so I just see the question in the chat about neededness redex. About neededness, for now we do not use for now the usual notion of neededness based on residuals and all that. So you can argue that if we substitute some term we have in our lambda terms by non-terminating terms, then you will break something that will not break in our calculus. So we use this kind of meta argument that if any non-needed redex in the lambda term can be replaced by a diverging lambda term, and our calculus will still find the normal form. So in this sense, we perform only needed reduction, but for now we have no complete formalization of residuals and all this neededness theory.
Okay, thank you very much. We have no more time. Giulio has another question, but maybe you can go to the discussion room and continue the discussion.
Yeah, sure, I will be there.
Thank you.